we're now going to extend our understanding of flux to include a calculus version of flux. Now, what does a calculus version of flux entail? It's going to use our same basic definition of E dot n hat A, but now apply it over all of these little discrete area elements that are going to become smaller and smaller and smaller until they become infinitesimally small area elements of a total surface. We're going to do a summation of all these area elements, and summation in calculus becomes integration to sum up all of the flux calculations through these little area elements to get the total flux. So let's kind of start at the beginning here. So we're looking at just a general curved surface. You can consider it like a saddle, for a horse. So just like some curved surface here. And what if we want to know, or have a way to know, the flux through this surface from some general electric field, E, that I have shown here. So we just have an E going here. And what if we want to know the flux through that total surface? Well, we can break that total surface up, as is shown here, into all these small discrete area elements. And we can put an n hat with each little area patch that makes up a portion of this total saddle area. And if we calculate the flux through one of those discrete area elements, that's exactly what we get. We get a portion of the total flux, this what I call delta capital phi. So now we can get an approximation for the total flux by just doing a summation of all of those area patches. So we get our approximation for the total flux through that area. And we then get our calculus version simply by letting those area elements get smaller and smaller and smaller. So in the limit that those area elements approach zero, right? So infinitesimally small, then our approximation is no longer an approximation, it's an exact answer. So when we go from the approximation to the exact answer, we replace all of this notation with the much more simplified calculus notation of integration. So that's why integration is the summation. We replace our discrete interval delta A with the differential dA. So it's not d times A, that's our differential dA. And there we have our calculus version of flux through the generalized area. And I'm going to clean this up a little bit. Up a little bit and get a nice box around here, because that is our general equation for flux that works at all times for flux, and we will be utilizing this when we introduce Gauss's law, which we'll be using much more in this unit to be able to calculate electric fields, as we will see. Now, before we do that, I have a couple pages of notes here. Just because I have found it useful for students to better understand this notion of an area integral generally. So even though it's really not mathematically part of our course, because as it's shown here, it's multivariable calculus. We have multiple variables. It's kind of the very basics of multivariable calculus, and if you understand calculus, you can understand the next lesson, showing you basically how it works, and I think it gives you a better feel for then applying this integral version of flux, which we will be doing a lot more of as we go through this chapter and through this course. So pause the video here, make sure you get all of your annotations down, and as always, ask questions should you have them.